Okay, so this is a set of notes on the properties of trapezoids, which are like kites. They're quadrilaterals that are not parallelograms. Okay, so a trapezoid is a quadrilateral that has exactly one pair of parallel bases, parallel sides. We call the parallel sides bases, and these are called bases. And the other sides, this one, let's make the arrow go the other way. That one and that one are called legs. This is a trapezoid. Okay, if you happen to have a trapezoid where the two legs are congruent, so these are parallel and these are congruent, this is what's called an isosceles trapezoid. And some of these things, specifically the isosceles trapezoid, have some particular properties. Okay, so the first one says that if I have an isosceles trapezoid, okay, so we'll call this thing A, B, C, D, and say that it's an isosceles trapezoid, then each pair of the base angles are congruent. So we want to say that like A is congruent to B and D is congruent to C. Now, what we're actually just going to prove here is that D is congruent to C. If you want to prove that A and B are congruent, just flip the whole thing over. Then you'll get, actually, I think we've got it all. We'll get, yeah, you get, excuse me. D is congruent to C. Actually, we're actually going to also prove that angle DAB is congruent to angle CBA. So we'll prove both sets. It's simple enough. All right, because this is an isosceles trapezoid, we know that these two are parallel, and we know that these two are congruent. So what we do is we drop in a segment here. There we go. And we drop in another segment here. And we're going to call this E, and we're going to call this F. Okay? Now, because of the way we drew these are 90-degree angles, right? So that's a 90-degree angle. That's a 90-degree angle, right? So that helps us. We know that AB and EF have to be parallel, right? So nothing surprising there. We also know that AE has to be congruent to BF, because if these lines are parallel, they have to be equidistant from each other. And at this point, I now have triangle DEA congruent to triangle, that's not the triangle symbol, triangle CFB, because we have the hypotenuse and the hypotenuse, and the leg of a right triangle, that's by HL. Okay, so these two triangles have to be congruent. That gets me that angle D is congruent to angle C, because D is in the one triangle and C is in the other. So that's by CPCTC. That gets me this. So I've got that proven. Well, if I take a look at this, I know that the measure of angle BAD, right, or DAB, let's call it that, DAB, plus the measure of angle D has to equal 180, right? Because these are parallel lines and that's a transversal. That's because they're same side interior angles. Likewise, the measure of angle CBA plus the measure of angle C has to equal 180, right? Well, that means that the measure of angle DAB plus the measure of angle D has to equal the measure of angle CBA plus the measure of angle C, because they're both equal to 180. And then these two, the D and the C, are equal to each other. So if I take that from one side and that from the other, subtracting something that's equal from both sides, I get the measure of angle DAB is equal to the measure of angle CBA, which is the other thing that I wanted to prove. If I have an isosceles triangle, the angles that are on the same base, the base angles, have to be congruent. So that's pretty straightforward. All right, so let's get a second property here. So the second property is also of an isosceles triangle. Okay, and what we want to say here, so if I call this A, B, C, D, the theorem here is that the two diagonals, AC and DB, are congruent. So we want to show that segment AC is congruent to segment DB. That's what we're going to try to prove. All right, so right off the bat, we want to show kind of what's going on here. We know that these are parallel, and we know that these are congruent because it's an isosceles triangle, or isosceles trapezoid, right? So we can get a little clever here. We're going to focus in on these two triangles. We're going to focus in on this one, DAC, and we're going to focus in on this one, DCB. Okay, so we're going to focus in on those two triangles. So if I look, I've gotten one side. This is congruent to that, so that works, right? I know that angle D and angle C are congruent because they're base angles, and one of those is in each one. And aha, that side is congruent to itself. So that will give me side angle side and side angle side. So the triangle DAC has to be congruent to the triangle CBD by side angle side. If I look, AC is in the first triangle and DB is in the other triangle. So those are congruent by CPCTC, which is what I've set out to prove, that the two diagonals of an isosceles triangle must be in fact congruent. So there you have it. Okay, so we do get one more property, and this doesn't actually have to be an isosceles triangle, but we'll prove this one out anyway. Okay, so this one does not have to be an isosceles trapezoid. It's actually any trapezoid will work. So let's build this so that these are not congruent. Okay, so we got that one, and we have this one. And what this tells me is that if I join, so we're going to the midpoint, so let's call this M, and let's call that N, and I put a segment in here, then the argument here is that that segment is 1, parallel to both of the bases, and 2, that the length, so like if I call this Q, R, S, and T, then the length of MN is the average of QR and ST divided by 2. All right, so how do I think in your notes this is actually SP, so let's use that as SP. All right, so QR plus SP divided by 2. So how do I do this? Well, I can do this using a coordinate proof. Is probably the easiest way to do it. So I am going to build my coordinate plane. I'm going to do this in such a way that P is at the origin. So P is at the point 0, 0. S is going to be at some point along the x-axis. So we're going to be kind of clever about this. We're going to say, in fact, that it's at Well, let's do this. Let's make Q at 2A to B. So what we're saying here is to get to Q, you've had to go to the right 2A units and then up 2B units. And I'm going to be careful about that. And then R is going to be here at C 2B. And that makes sense because these both have to be at the same height, right? Because if these are parallel, those have to be at the same height. But that can be 2A and that can be C. Now, this one's to the further to the right than C, so we're going to say that this is C plus, let's call it 2D. And then the height of this one is 0. Okay, so let's see, where does that put M? Well, M has to be halfway between these two, so halfway between 0 and 2A is A, halfway between 0 and 2B is B. Okay. Halfway between C and C plus 2D. So C plus C plus 2D. Halfway is 2C plus 2D divided by 2. That makes that C plus, oops, that's not C, C plus D. So the x-coordinate here is C plus D. And halfway between 0 and 2B is going to be B. Okay, so we have a coordinate for M and we have a coordinate for N. Now, here's what we note. First, this has to be parallel. Why does it have to be parallel? Because this goes from 0 to 0, which means it's horizontal. This one goes from 2B to 2B, which means it's horizontal. This is going from B to B, which means it's also horizontal, which means that all three of these lines are parallel to each other. Now, finally, we get a little bit of a game here. It's like, how do I show that the distance from QR plus SP divided by 2 is MN? So let's take a look at this. The distance QR, so let's get some room here. We're going to have to do some mapping. So let's cut that out. All right, and take it away. And let's start mapping. QR is the distance from 2A to C, so that's going to be C minus 2A. SP is C plus 2D minus 0, so that's just C plus 2D. So QR plus SP over 2 is C minus 2A plus C plus 2D all over 2. So that should be 2C plus 2D minus 2A over 2, which is C plus D minus A. Okay, so we have a calculation for QR plus SP over 2 is C plus D minus A. Okay, well, let's look at what MN is. There's no change in the B, so we just take the C plus D and subtract the A. And lo and behold, MN is C plus D minus A. QR plus SP over 2 is C plus D minus A, which is exactly what we're saying here, because these two things are, in fact, equal to each other. They're both equal to this C plus D minus A. The way we've set up the coordinates here, we see that the three things are all parallel, that the mid segment is in fact the average length of the other two. So let's summarize real quick everything that we've said in this video. 1, trapezoids have two parallel sides. 2, an isosceles trapezoid has two congruent sides. If it's isosceles, then first, the base angles have to be congruent. Second, the diagonals have to be congruent. And for any trapezoid, it's mid-segment, that thing that connects the two midpoints, right? So M is the midpoint of this side, and N is the midpoint of this side. Has to be first parallel to the other two sides, and second is the average length of the other two sides. So there you have it.